Okay, so I'm going to try and walk through some HiC analysis using HiC Pro and HiChipper. This may be a little rough because this is kind of a weird, complicated walkthrough, but we'll give it our best shot here. I wonder if I can blow up the font here. There we go. All right, so the way this works is first thing you do is use HiC Pro to create your kind of, what are those files called? They're like bed PEs. So essentially it's a bed file, but instead of having one location coordinate, you have two location coordinates, and that specifies that it's a loop. And then what you do is you take that and you run it through HiChipper, which gives you kind of more quantitative results. And it's going to be a little tricky because the analysis is of big enough files that I'm not going to be able to do it here to show you how it goes, but I'm going to be showing you some stuff from that we've worked with, that HiC's made some HiChip libraries. Kind of show you what the outputs look like and what the setup looks like. So the first thing you do is you need to run HiC Pro, and to run HiC Pro you're going to need a resfrag bed file, and depending on what your restriction enzyme you used was, you may need to build this, you may not. So I'll give you an example of the HIND3 fragment. So I have a program here that I wrote called make resfrag bam. Should probably be make resfrag bed. So if you have my bin file in your path, then this will show up. The way you can add my bin file to your path is you do path equals $path tilde use 6004424/bin, and that'll add my bin to your path. And then you can just do make resfrag bam.py. It'll give you this usage message. So the way you use it is you got to tell it what genome you're working with, what the sequence for the restriction site is, and then how far into that is the cut. So for example, HIND3, you're going to say, okay, here's my program name. The genome is HG19. Here's the sequence for the HIND3 cut, and you can see it cuts after the first A. So the cut site is 1 in. If it were halfway through, it'd be 1, 2, 3 in. And then the last argument is the output name, which here is HIND3 bed. So I think this program runs fairly fast. Let's just run it and see what happens. Could be magical. So you can see it's crunching through those chromosomes pretty fast. I could probably make it run even faster, but I don't know. I feel like 30 seconds to 40 seconds isn't too bad of a wait time. You can see we're almost done here. All right, so now we should have this HIND3 bed. And so this is just a bed file with all of the restriction enzyme sites. I might change it to add this, but it's not a bad idea to sort this correctly so that 10 isn't the first one. And you can just do this by doing that. This may take a second, not too long. And did I lose it? So now you can see it's sorted correctly. Anyways, so now that you've got that, you need to make a configuration file. So I'm just going to go over into HiC's stuff and we'll look at this. Oh, so if you're wanting to do this, I've got in my home folder this this folder with kind of template files for everything you need. So I've got a this is the configuration file here. I've got the image file, which you'll need to run HiC Pro. And then I've also got a YAML, which we'll talk about here in a second. So let's go ahead and look at the config file. So there's not a lot you need to change in this. Most of it you can just leave alone. But stuff you need to be aware of is the ligation site needs to be your restriction fragment, as well as your genome fragments need to be you need to give it the path to that restriction fragment that we just made. So you give the path to that, you got to give it the sequence of the restriction site. I don't think you need to touch any of those. The other thing you might want to change is the bin sizes. So this is just basically how much resolution you want it to generate the final file with. Like the default lowest number is 40,000. And that gives you a lot of signal in a bin, but it's not very good for seeing what's going on up close, which is what we've been working with. So we do around 5,000 base pair bins, and so you can do multiple. So we just do 5,000 and 10,000. But I think those are the only two things I really change. The rest of this should be okay. If you're not doing HG19, there is one more thing you need to change, which is your reference genome and this location here, as well as the bow tie indexes. So it uses bow tie 2, so you'll need to give the correct path to whatever genome's indexes you're using. Okay, so with that said, let's go over to HiC's stuff and I'll show you kind of how we did this. So to run the program uses Singularity, and you're also definitely 100% going to want to run this inside of a on a node. So I wrote a wrapper called hicpro.sh, and you can see if you run this. Here, let's just do this bash. So all you got to do to give this is you got to give it the location of the FASTQ folders, which I'll explain in a second, an output folder, and then the config file location. I've got the parallel option in there, and don't use that. I've taken it out. I'll modify this program to not put that in there. So don't worry about that. So HiC Pro, what it wants you to do is it wants you to take all of your different things that you're combining. So you're going to have paired end reads for this, and you should have probably multiple ones. So you'll have one set of paired end reads for each kind of experiment you did, and it expects you to put all of your experiments into a single folder, and then you can use that parallel option to run things in parallel. It's kind of messy. It's supposed to work with Slurm. It doesn't work great. So what I do is I create a folder for each experiment, and that's why this is going to look a little goofy. But so like, for example, if we look at the folder she's got here, you can see there's a few combined ones here. So let's see here. YouTube. It's different. Okay. So like, for example, we did this experiment here. So we have the folder called 17819x2, and inside it we have a second folder called 17819x2. So what normally you would expect to do is you'd have the outer folder called something like, you know, ER high chip, And then this first one would be called ER plus, and you'd put your two passkeys in it, and then you'd have the ER negative one, and you'd have your two chips in it. But essentially, we're just keeping everything separate. So we just have two folders with the exact same name, and inside the second folder is the passkey file, and it can be gzipped. You don't have to unzip it for this. So essentially, you just make a two-layered folder which both have the same name, and then you feed that top folder to HiC Pro. So for example, for this one, I would for our example, I'm losing my mind. Okay, bash. Answer is yes. So what we do for this example is we'd say bash HiC Pro x2. So that would be the passkey folder. The out, I think we called just a simple name out. And the config file, we just called that was the my5k config HiC Pro. So this is literally all you have to do. So that's kind of the setup, and what's going to go on underneath the board is it's going to grab those arguments you got in, and it'll say, first it'll check to make sure you're on a node. If you're not on a node, it'll automatically log on. They'll run through it and say, ooh, am I running in Singularity or not? If you're not, it'll fire up Singularity, it'll load Singularity, and then fire up Singularity, which will run this all again, but it'll execute it using that HiC Pro image. So this has a bunch of stuff inside of the Singularity package to make sure the program runs correctly. Doesn't always run correctly, so if you run into errors, let me know and I can kind of help you troubleshoot that. It's mostly has to do with Python packages, but I think I don't know, I'll have to double check, but I think everything is set up right for that. All right, so that will take quite a while to run, probably about a day. You'll do that for every single FastQ pair that you have. You'll do them each individually, and you'll wait for that to run. And then once that's done, then the next program you're going to run is HiChipper. And what HiChipper does, let's see if I can remember what HiChipper does. Let's just look at what the output from HiC Pro is. So the output from HiC Pro, do this. So sorry, this is kind of a tree view. You get a bunch of dams that it makes, and it gives you all the unmapped reads and a bunch of stuff that you'll probably never use. But some stuff that is useful, I think that gives you is these your paired that you've got here. And I swear there was one other one, but that might be HiC Pro that puts it out. Oh, these iced files are useful. Like I said, it's been a while since I've looked at this, so I apologize if this is very confusing. Okay, so next we're going to run it through HiChipper. So HiChipper is looking for the setup that HiC Pro puts out, so we don't have to mess with anything at this point. So all you have to do for HiChipper, so let's look at this So I have what's called the HiC chipper wrapper written, kind of like the HiC Pro.sh, and sorry, sometimes it's hard to get out of them. So let's look at this HiC chipper wrapper. Okay, so all that HiC chipper wrapper is doing. So this is the one I think that actually runs into some problems, but we're just grabbing this YAML file and this output file name where you want to spit out, lock you onto a node automatically, so you don't have to worry about that. Yeah, there's not much to it. I grab a couple of these things just to make sure it's pointing to the right position. But yeah, like I said, there's not much to it. Mostly all you got to worry about is this YAML file. So let's look at the YAMLs. The YAML means yet another markdown language, which is basically saying we made this for no reason. It's very annoying, but whatever. Okay. So if we look at this one, it's wanting to know how it wants us to call peaks, because HiChipper is basically looking at how peaks are connecting to each other and kind of giving us some QC from that. So we actually want it to call its own peaks, kind of like Max would. So you can read more about that here. But typically what we're doing is we're just looking for self-ligating pairs, and we're using those to call the peaks. And then it's using all of the different conditions. So that's what the combined self means. And like I said, you can read more about that right here. That's actually a really good resource, and I would suggest reading it to understand what's going on. Then it wants a restriction fragment bed that we created. So you give it the path to that. I would just stick it in the directory you're working in. And then it wants the folder that HiC Pro put out. So you just give it the path to that. And then that's all you got to do. So you just create that file, call it whatever name you want, and then you just do HiC HiChipper wrapper.sh. You give it your output folder name. So I think in this one we gave it the DMSOERSS combo self-ligation. That was the output folder name, and then we just said DMSOER for the YAML file, and that's it. And that'll take a long time to run as well. If it doesn't take a long time to run, it probably didn't run right. So you need to look at it a little closer. Like I said, let's look at some of the outputs. It's a little confusing, and it would help if I made these right after I finish, but this is live. So some of the outputs that HiChipper is going to put out is like, say, this anchor file. So let's see here. So the anchor file that you really want is this. I think it's this interactions one, but that doesn't look right. But essentially, this is like a the chip binding sites of what you were looking at. So these would be like ER binding sites. And this might give you a bit of an overrepresentation. Like, I guarantee you there's not 120,000 ER binding sites. So you got to be careful when you're using this. But it can be helpful if you look at it a little more stringently. Other file that is useful is this bed.de file. So you only want the filtered intra loop counts. So this is showing you this position was looped to this position. And I think I gave these or this is the number of those loops that you found. So this is that kind of the size fragments that were generated by HiC Pro. This is saying from region on the left to the region on the right, and then the number on the far right side here is how many like binding events you've got here. And it's sorted by position in the genome. So this is the other thing that you may need for your programs. So again, sorry if this is confusing. If you have questions, ask me. If it's a big question, it's important, I'll kind of edit this video and you can go back and use that. All right, good luck everybody.